Okay, hello everyone, and we are going to be now the fourth Open Zemi. This is an exercise where our research group makes presentations from the participants to talk about our research topics. Today I have Jair Pereira, a doctor first year student, who will talk about comparing meta-heuristics by clustering. So
Thank you. So hi, my name is Jair. I'm a first year PhD student here at the University of Tsukuba. And today I'll introduce my research topic that is on meta-heuristic algorithms. So let's get started. First, what is it? Those algorithms, they explore search spaces like this one here on the screen, and it tries to find the minimum or the maximum values in the landscape. So in this example, we want to find x1 and x2 that will lead us to the blue peak here on top. Some search spaces are hard to explore, and one algorithm may not find the best solutions. In many situations, we don't even know beforehand how the landscape looks like. About the algorithms, you probably know some of them already. For example, genetic algorithm, particle sort optimizations, and many others. So the question becomes how those algorithms work, how do they explore search spaces? Well, all of these algorithms have a certain similarity. There's a kind of template. We first sample the search space by creating a set of random candidate solutions, those black dots here on the screen. Then we evaluate all the candidate solutions, meaning we check how good they are, illustrated here by the red arrow. Then, until we meet some termination criteria, we sample again the search space based on the information we got from the previous iteration. In other words, we update all the candidate solutions, evaluate, update over and over again. The main difference among meta-heuristics is how this update is done. So different algorithms have different search strategies, different ways of doing this update. Well, but there are some problems here. First, actually it's not a problem, it's more of a characteristics. Different algorithms perform best on different types of problems. And now we come with three problems. First, there are over 200 algorithms. So if I want to solve an optimization problem, which one should I choose? There are just so many. Another problem is that most of those are described in terms of metaphor. So it makes it hard not only to implement the algorithm, but to compare to others. And the last problem here is that most of those algorithms are very similar to each other. And this is related to the previous problem, because if you describe them in terms of metaphor, you cannot compare them very well. And you can hide some details in the implementation. So in this context, it's important that we can effectively compare algorithms and search strategies. So we want to go beyond the metaphor and answer how can we compare algorithms, compare search strategies, how similar are two algorithms, how similar are two search strategies. Let's go to the literature, see what other researchers have been doing here. So there have been efforts in this direction. Here I have three works, two from Loans, one from Armas. They each categorize some meta-heuristics based on how they explore the search space. They have a list of search strategies. Here I have a table, each column, one of the search strategies of each of researchers. And here I'll give an example of how they categorize the algorithms. First, let's get loans intermediate search. Let's zoom here in this area of the search space. And an algorithm that do intermediate search will choose two candidate solutions, those two that I zoomed here. and generate a new solution within this shaded area that's in between of those candidate solutions. And that's basically the crossover in the genetic algorithm. Let's pick one more example now from the other part of the table, the follow the best. Again, let's zoom here, the search space. Now we have the triangle, that means best solution found so far, and the white circle, that's the solution that we want to update now. We basically draw a distance vector towards the best solution and use this to guide this solution towards the best. So we see on the table here also other strategies like follow the best, follow its own best, follow the neighbor. All those strategies are different ways of drawing this distance vector. And each of those are a special type of what Loans call directional search. So ARMAs focus on swarm algorithms, whereas Loans have more general categories. Okay, moving to the next part. Another nice thing in ARMAs is that they compute a similarity score between the algorithms. So to compute this score, in very simple terms, they count how many search strategies those algorithms share, and they present figures like this one here, where we see PSO is quite similar to ATA and RIO. And this is based on how many of those search strategies they shared. Now, let's get to my current research. So the idea I'm working right now is that I still on how to compare two meta-heuristics, but I'm comparing them inside a context. So I said that search strategies are how an algorithm explores a search space. For me, we cannot tell the whole story by looking at the search strategies alone. More than that, I want to draw a relationship between search strategies and types of problems. So what am I doing right now? I have algorithms and I have problems, and I link together the algorithms and problems. This link is the execution. So I run, say, PSO on problem A, problem B, problem C. Now I can use this information from those executions to classify the algorithms. And I said information, it's not so specific. And that's because we could use many things here. The first thing that comes to mind, for example, is the objective function. That's a performance indicator. And why? Well, it's reasonable to expect that similar algorithms will perform similarly on different problems. And we may have other indicators also, for example, the unique solutions that the algorithm found so far during the execution, or the path of the best solution towards the optimum. And then we can use those informations to classify the algorithms using cluster. Okay, it may seem a bit abstract so far. So let's say I chose these algorithms here and those benchmark problems here. Then I run our algorithms on all those problems, and I will have a table like this here. So in this table, the columns are the algorithms and the rows are the problems. And each of those values is the error to the optimum. So one execution basically. And I use this table as feature to cluster the algorithms. So here I'm plotting a two-dimensional PCA. And there's some interesting things here happening. Let's move to the next slide. So at the right side, we have the work from AMAS, a plot of the similarity based only on the search strategies, not considering this applied to a problem. And on the left, I have a plot of the PCA of the algorithms run on many problems. So it's quite similar, those to what we see here. I just want to call your attention that those are early results I had a very limited number of repetitions of budget. So I won't draw many conclusions from this yet, but we can see that there's something interesting and worth investigating here. I've done similar process to cluster problems, and I also got some interesting results, but maybe this is for another time. So thank you very much, and I'll be happy to take questions now.
All right. Thank you very much, Jair, for your presentation. Hello, everyone. And as usual, we'll first take questions from the people who are here on the call, and then after that, if there are any questions from the YouTube chat, we're gonna take questions from there. Hello, Felipe. Our honor guest today is Felipe Campelo. Hello, Felipe.
Hi, Klaus. How are you doing?
Good. Thanks. Thanks for
Hello,
joining
Jair.
us.
Hello.
Thank you for inviting me.
Yeah.
And thanks for the presentation, Jair. It's very interesting.
Well, would you like to start with any sort of questions or comments to Jair, Felipe?
I would, since you put me in the spotlight there.
Of course I did. No, but just to level, like the idea here is that we have everyone ask questions. So I usually start with the PhD students, then the master students. But since you are the most senior of them here, then I'm gonna put you on the spot last first.
The most senior is a polite way to tell me I'm old, I suppose.
Exactly.
So what time is it for you now? Is it 4 p.m.?
Right now it's 5:40.
5:40. So
Yeah.
For me here, it's 8:42 in the morning. So good morning or good evening for you folks. Jair, I have a couple of questions, and they are just to first of all, like I think the topic that you're exploring there is quite worthwhile. Like it's an interesting thing, and it resonates well with something that Klaus and myself and others have been discussing for some time, which is the need for a more quantitative, a more structured way to look into meta-heuristics. And two questions that I have, like one is a curiosity, actually both are emerge from curiosity. First one is the way like Jessica de Armas and Loans do their classification or their similarity measurements between different...
I'm sorry, it was cropping. Could you repeat, please?
That's all right. Jessica de Armas and Stephen Voss, who wrote that like paper earlier this year, and Loans as well, who wrote it, I think, last year. Both of them, they concentrate on very specific versions of the meta-heuristics that they are comparing. So you can think of a genetic algorithm, for instance. You have a sequence of operators. Like you have like selection for reproduction, you have crossover, you have mutation, you have a selection for next iteration. But within each of those steps, there are many different ways that they can be implemented. If you take a look at the literature on crossover operators for genetic algorithms, for instance, there are like hundreds of variants there, which suggests that we may have two levels of similarity. We may have a level at the framework level. That's the one that I just described. So we have selection for reproduction, crossover, mutation, selection for survival, and another level of similarity within the that takes into account the choices, the instances of the meta-heuristics. How do you think these things could be reconciled? So the framework that you're thinking here, and I think it's a very good idea to cluster the meta-heuristics using their performances on different classes of problems. I think it's a great idea. But how would that be affected if you had a different crossover operator, for instance, for genetic algorithm, which could change the performance of that algorithm for different classes of problems and probably would change the performance? Do you have any ideas on that?
Yes, that's actually a very interesting question because now I'm thinking about it. I'm not actually comparing the algorithms itself, but I'm comparing the implementations of those algorithms. So it's if I add the genetic algorithm here, I'm not comparing genetic algorithm, but this specific one that has this crossover and this mutation. And this also relates to the choice of parameters. Like
Yes.
if we change parameters a little bit, the behavior of the algorithm can change a lot. And
Yes.
yeah.
And that is something that has always confounded people when trying to quantify and model meta-heuristics, because meta-heuristics is a very broad umbrella. And if you go to the basic definition that Fred Glover gave there in the 80s, I think, it's essentially the framework. It's this big framework from which you instantiate methods that are custom tailored for each specific problem. If you're trying to do a more general like comparison, like the ARMAs did, like Loans did, it's important to define, like as a first step, to define very well, very precisely at which level exactly you're comparing. And you're right there, you're comparing implementations under certain values of algorithmic parameters. And those like are structural parameters, like the choice of the operator that you're going to be using for crossover, for mutation, for any other type of search. And the second level are the values of the quantitative hyperparameters that go in there. And I would be curious to see, for even within, as an extension of what you're doing right now, even within a single meta-heuristic class. So again, take genetic algorithms. How those, like, how do you cluster different genetic algorithm variants based on their performances on those same classes of problems? Are they a compact cluster that essentially like stretches on the space of performances, or are there different clusters in that space, signifying that the algorithm can have like this sort of phase change, this sort of like abrupt transition in behavior when it is trying to solve like this problems that you're using as a basis for your experiments there. So there are quite a lot of interesting questions that can be asked based on the idea that you are that you're exploring there. I like it. I like your topic quite a lot. There's a lot of potential in there.
Let me just go back to this slide. I want to do this. I'm thinking of doing this, not with genetic algorithm, but with PSO. It's something similar, where PSO has, for example, follow the best, follow its own best, and if I'm not wrong, guided move based on previous solution. So my idea is to shut down each of those strategies. So I have different types of PSO that I don't have it's lacking one of those strategies.
Yes.
And I would compare this. So similar to ARMAS, I'm focusing more on swarm. I wasn't considering genetic algorithm, but no, it's still very interesting too.
Yes, that is absolutely all right. It's essentially like the idea is the same. It's just the algorithmic framework is slightly different. So you're exploring PSO, and that's absolutely legitimate. I just used GA as a basic example. What you mentioned there of shutting off one component of the algorithm at a time and checking the performance. And Klaus will tell you all about that because he teaches experimental design there on your end. It's called the one factor at a time design. And that will be interesting for you to test or for you to isolate what's called the marginal effect of that operator. So like what happens if that operator does not have interactions with the others, but its like effect can be separable from everything else. If there are interaction effects, so for instance, if follow the best and follow elite, like independently, their presence or their absence have certain effects, but when they are both part of your method, they have like a compound effect or they have an interaction effect. This sort of shut one off at a time strategy does not necessarily allow you to discover that. Again, it's not a problem, but it's a limitation of how far you can go with your question answering based on your experiment. But like I'm preaching to the core here because Klaus will know all that there is to know about factorial experiments and how you could refine that. So I should probably at this point just thank you for your presentation again and give the mic back to Klaus so that others can ask you questions as well. Otherwise, I will monopolize your presentation.
Well,
so thanks a lot for the presentation there.
Monopolizing the presentation is why we have special guests. But thank you for the points, Felipe. I just want to add something. I think it's one thing that is interesting is that even it's kind of going back on a recommendation that I gave Jair this morning, which is going back on why he's doing this clustering. Which the idea of doing the cluster comes from because on the master degree, Jair was working with automated algorithm design. And when he was doing automated algorithm design, the question was, which components do we add to the design? And one way to do that was to do the cluster. One way is to do the clustering, and from the clustering, try to identify which components have the biggest influence in changing the performance of the algorithm. So that's one point that we are working with on this particular question. But I will just go back to the questions. And thank you again, Felipe. And so next I would like to ask Yuri. Yuri, do you want to make some questions or comments?
Sure. Thank you, Jair, for your presentation. And I would like to ask you, what is
just a second. My internet is cropping a bit. I will stop the video just to get a better audio.
Sure, no problem. So what's if everything goes well and you get the results and experiments and you can cluster algorithms in different clusters and find some comparisons, what do you think would be the takeaway message from your work?
Well, first, Klaus commented something already. Actually, I removed last minute because when I was practicing, it didn't fit the timer, but when I presented, I was so nervous that I went so fast and actually had time to add this. So in my master's, I work on automated design of algorithms. And then back there, I chose the algorithms I knew the most famous one. But that's not a proper approach. So the question is, how can I choose a set of algorithms that they have different search strategies, different behaviors? So a representative set of algorithms that I can use as a component to create a new one, specifically to my problem. Another thing is that when we compare those algorithms and we see that they are very similar to each other, then we see, for example, if this PSO and ATA, they are very similar, we see that maybe this ATA is not worth, like implementing is not worth using it if PSO is more classical and do the same thing. Did I answer your question?
Yes, you did. I'm just thinking a little bit about it. Okay, yeah, thank you very much.
Thank you.
All right, thank you very much, Yuri. Next, I would like to ask Ifan to make a question or comments.
Yeah, so first, thank you very much for the presentation. I want to ask, how did you select the algorithms and problems you tested in your experiment?
Okay, this was actually just a pilot experiment, so I didn't consider too much about why I choose those. So I got basically the ones that I follow the similarity that I saw here in ARMAS. And I added also Firefly algorithm in the set. About the problems, well, here I have only the numbers that they use in the benchmark. But this first one is the sphere. So I use more as a, okay, if my implementation is solving sphere, everything's all right. And then I have pairs of problems, 3 and 8. They are the same function, but with some difference in the implementation. I'm sorry, 8 and 9 are the same. 3 and 15 also are the same. They are Rust string. And the difference is that, for example, 3 is separable and 15 is not. So I have another pair, 17 and 18, and 21 and 22. So I didn't do this part yet, but my idea is that I make, maybe I can get some information since those are basically the same function with some differences in the structure. So maybe I can get some extra information by analyzing them. And this is what I commented that was a bit interesting. I didn't show during the presentation, but is that when I cluster the problems based on these executions, I got those pairs of functions quite close together. This is PCA. This is just a representation. Well, did I answer your question?
Yeah, I see. I think, yeah, I understand what you are saying. So another thing is I want to say, so these clusters, they are based on the relative distance. Is it possible for you to find a baseline for these clusters? I mean, for example, if you include another algorithm, then you find actually these 5 algorithms, they are quite close. Is it possible to have a baseline for this comparison?
Mm. Oh, I have to more about this. Um, this is one of the reasons I'm plotting the PCA. I also added the color, that's the clusters of k-means, but I'm not making it so important. I'm more looking how they distribute here in this 2D plot. Because if I add another algorithm, then there'll be, for example, many more executions, and how those relationships here will change also. So it's something I still have to mature a bit more, this part.
Okay, I see. Thank you again for the presentation. That's all of my questions.
Thank you too.
Thank you very much, Ifan. And I think this result, although you didn't talk about on the presentation, this result of clustering the problems based on the performance of the algorithms and seeing that the problems got close to each other. I think this is actually really interesting as well. It's not your main goal, but I think it's interesting if you dig a little bit and see what you can find about it. So finally, I want to ask Abe to make some question comment. Abe, go ahead.
Yeah, thank you. Firstly, maybe my question is a bit naive because this is not my research area. But so from what I get is you try to cluster the type of algorithm based on the uh, types of it. But my question is, do you cluster it using the result of your run on the problems, or you cluster it based on the characteristic of these algorithms?
So I could cluster based on the characteristics. For example, we have this table here, right, with each of the search strategies. So I could have a column here, PSO, which strategy does it have? ATA, which strategy does it have? But I think this would be very similar to what ARMAS did in a different way, but would achieve the same result. And so what I'm doing is on the execution itself. So I run PSO on all those problems, and I have the value it got from the execution.
Okay,
And this
so
is what I use as a
I see.
feature for the cluster.
So that leads to my second question. Is there any study that already clusters these problems, these what we call the benchmark problems? like for example, it's clustered by the characteristic of this problem itself, like it have a single big optima, like global optima, or many local optima, etc.
I'm not sure if there is a work I'm not aware of, but in the benchmark, they group those functions together based on their characteristics because, well, it's benchmark function, so they know very well the landscape and how the characteristics of the landscape. So for BBOB, we have 5 groups of functions that share some similarities.
I see. Yeah, because I could see that if we have like a certain separation or a clear separation of this group of problems, we could map like if the characteristic for like each of the, if we found like a similarity between the one group of algorithm in a specific group of problem, then maybe we could we could map the characteristic of the algorithm itself to the characteristic of the problem itself, right? I think that's your goal. If am I wrong or not?
Yes, this would be very nice if I can reach there, that I say, okay, this search strategy is good for this type of problems that has this characteristic. But I think there's still a long way to get there, but it would be very nice too.
I see. Okay, that concludes my question. Thank you very much.
Thank you.
All right. Thank you very much, Abe. Okay, so everyone got their chance for a first round of questions. We don't actually have any questions from the YouTube chat today. So anyone would like to make any final questions or comments? Yeah, Felipe, go ahead.
Hi again. The one thing that just crossed my mind here is that if you're using some of the same algorithms as Jessica de Armas and Stephen Voss used in their paper, right?
Yes.
So in that paper, they show a table of similarities that they have derived based on their classification, based on their ontology of algorithms. And if you use that table, you can actually calculate a hierarchical clustering of the algorithms, not based on results, but based on their modeling of those algorithms in terms of their components. I would be very interested to see how your performance-based clustering aligns with the structure-based clustering that is possible to build based on their similarity matrices. Because like you could have surprising results in either direction. It could be that the performance-based clustering would align very well with the structure-based clustering, which would just like be 2 independent lines of evidence to reinforce the similarities of those methods, not only in terms of structure, but also in terms of behavior. Or it could be very surprising to the other direction. And like you could just find out, okay, like minor differences, even very similar algorithms based on structure can lead to very distinct performances when they are actually run on problems. So I don't know if you thought about like since you're using the same algorithms, the dissimilarities based on structure are already there. They have been calculated for you. And it would be interesting to see.
Actually, yeah, this would be very nice to check this. I'm currently running those experiments with more repetition, so it's more robust. And maybe on next step, I can actually compare to Jessica de Armas.
Yeah.
And yeah, I'm aiming for a Gecko or SEC, so I'm currently running those experiments and analyzing.
Yeah, if you're aiming for C or Gecko, you're like working on a time budget because the deadline is late January usually, so you don't have much time for that, right?
Yes.
Okay. Just so this idea of clustering, by the way, it's not a new thing. Like when the paper was published, when the Armas paper was published, Stephen Voss sent it to a group that myself and Klaus are part of, and I wrote back to him and I sent him the image that I just pasted on the chat here. which is exactly, I just did that. I got their similarity table and built a quick hierarchical clustering. And like he mentioned that he planned to do something similar in one of his upcoming papers. So it may already be out there. It's something to check, and it's easy to check in the like citation like tree of the Armas's paper if there's anything that cites that work already. But so if you're going to do like to include clustering based on a structural similarity as part of your paper, it's good to check if it hasn't been done before. So just a heads up there.
Oh, I'm gonna check though if there's some new work on this too to be aware of.
Because it's very easy to do, and it provides a very nice visual summarization and some structural insights as well. So there we go. That was it from me, Klaus. Thank you, Jair, again for your presentation.
Thank you very much for the discussion. It was very insightful.
Okay, thank you, Felipe. Thank you, Jair. Anyone else would like to share some final ideas or comments? All right, so thank you, everyone, and I'm going to end the open session today. Thanks everyone for watching, and this will be the last Open Zemi for this year. We will pick up in January, so everyone have a nice end of the year. Bye-bye. And this is the end of the stream. Okay.